Okay, let's go ahead and get started. So let me just begin this class by setting the stage for where we've been in this course and where we'll be going for the next few weeks. So for the first 3 to 4 weeks of this course, we explored the basic formulation of the theory of special relativity and its consequences. And in particular, we realized how the theory of special relativity can be formulated in terms of the geometry of Minkowski space. That is to say, through the geometry of space-time, where space and time are regarded on roughly equal footings. In particular, we found that the basic object of interest in special relativity was neither the spatial separation between 2 points, nor the time separation between 2 points, but rather this particular combination known as the invariant interval. I should mention something about this formula which I forgot to mention in previous classes. So there are two competing conventions on the sign of the square of the invariant interval. This convention that I use, where the invariant interval squared is delta x squared minus c squared delta t squared, is what's referred to as the mostly positive or West Coast sign convention. Whereas in, for example, the book by David Morin, I think he uses the mostly minus or East Coast convention. So just like in gangster rap, there are East Coast versus West Coast factions. Despite my desire to maintain consistency with the textbook, I couldn't bring myself to use the mostly minus convention. I find it morally repugnant. But you should keep in mind that you will see in your lives as physicists most likely both sorts of conventions. I actually don't remember what Bernstein uses, whether it's mostly positive or mostly negative. So having spent the last couple of weeks diving into the details of the theory of special relativity, I would like to now spend the next week and a half understanding some of its most basic consequences and most important consequences, which is that for the dynamics of systems, and in particular, special relativity will modify the way that we think about energy, momentum, and various other essential quantities in Newtonian physics. This is a subject that will occupy us for roughly the next 2 weeks. After which, we will dive into some of the slightly more advanced topics in relativity. I'll tell you a little bit, hopefully, about the unification of the forces and how we can begin to understand that through the formulation of special relativity. I'll talk a little bit about general relativity and cosmology, and that'll bring us to about the midterm of the class, after which we'll dive into a study of atomic physics and quantum mechanics. So let's start then by a discussion, or at least a reminder, of some of the basic principles of dynamics in Newtonian physics. So I think it's safe to say that one of, if not the most basic principle of Newtonian dynamics, perhaps even more fundamental than the force law F equals ma, concern the conservation of energy, which in Newtonian physics is 1/2 mass times velocity squared, and momentum, which is mass times velocity. So if you have some collection of objects with some masses and some velocities, from this description one can compute the total energy of the system. And you know that whatever processes this system undergoes, forces interacting between these parts of the system and so forth, at the end of the day, the energy and the momentum of the system at late time must equal that at early time. And here I've given you the formula of energy and momentum for just a single particle with a mass and a velocity. But of course, one can generalize these notions considerably. You can think about a rotating body with some moment of inertia, which will also carry some energy and momentum related to the moment of inertia or the inertia tensor of the system, along with its angular frequencies. If you have electromagnetic fields, then those electromagnetic fields themselves will carry some energy and momentum. And so this notion of the conservation of energy and momentum is really not so much a consequence of Newtonian physics, but perhaps the most basic postulate of Newtonian physics. So this can't really be derived. In a sense, it is a postulate of Newtonian physics. Now, for example, if you were to formulate Newtonian physics in terms of force laws, F equals ma, and to write down some formulas for those force laws, then from that formulation you could derive the conservation of energy and momentum in that specific situation. But really, I think it's fair to say that the assumption of conservation of energy and momentum is as fundamental as any other assumption that one could use to formulate the laws of mechanics in Newtonian physics. And so this cherished set of principles is one that we would like to preserve when we move from Newtonian physics to special relativity. And it turns out that in special relativity, the energy and momentum of a system are still conserved, but they take a slightly different form. In particular, the energy of a particle with some mass and velocity is no longer 1/2 mv squared, but rather it's mc squared divided by the square root of 1 minus v squared over c squared. And likewise, the momentum of a particle is no longer the mass of the particle times its velocity vector, but rather that quantity, again divided by this relativistic factor, 1 minus v squared over c squared. Where m here is the mass of the object, and in particular, as we will note in more detail later, it's what's referred to as the rest mass of the object, namely the mass of the object as measured in a reference frame where the object is at rest. And I make this distinction because there's a sense in which the mass will depend on the frame in which it is measured. I should comment here that this is the form of the energy and momentum of an object in special relativity, regarded as a function of its mass, its rest mass, and its velocity. And so this relativistic factor, the square root of 1 minus v squared over c squared, is appearing in a slightly different context from which it has appeared earlier in this course. Previously, this factor gamma, 1 over the square root of 1 minus v squared over c squared, arose when we were studying the differences between quantities as measured in frames which were moving with some relative velocity v. Here, v is referring to the velocity of some object, of some particle. And E and P refer to the energy and momentum of that particle as measured in some frame, namely the frame where it's moving with the velocity v. Okay. And there's a sense, as in the formulation of Newtonian physics, that these expressions for energy and momentum can't really be derived per se. They're really more postulates about the form of dynamics in special relativity. But they can certainly be motivated in some ways, and that is what I'm going to do for the rest of this class. Question?
For the energy?
Yes.
Shouldn't that be a 1/2?
No. Okay. Now, there's an important, that's an excellent question and an important observation. So in Newtonian physics, we denote the kinetic energy of an object as 1/2 mv squared. And here, what I've written down is not just the kinetic energy of the object, but the total energy of the object. Okay? So if you want to understand the relationship between this and your previous understanding of the kinetic energy of the object, then you would have to Taylor expand this expression for small values of the velocity, and you would see that one of the terms would be 1/2 mv squared, the kinetic energy. Okay. I'll comment on this in much greater detail probably by the end of this class, but that's actually a very important observation and one that we'll be getting to. Yes. Good question. Yes?
I'm slightly confused with what you said here. You said M is rest mass, but energy and momentum are as measured in.
These are the energy and momentum as measured in some frame where the particle has velocity v. And m is a parameter that describes the properties of this object, which we call the rest mass. And what is the rest mass? The rest mass is the mass in the frame in which the particle is at rest. So we would need to talk then about how you would define the mass of an object in a frame where the particle is moving. Sometimes people talk about this as the relativistic mass instead of the rest mass. That's not a language that I tend to prefer. I prefer to talk just about the rest mass and the energy, but we'll get to that. We'll burn that bridge when we come to it. Yes? Question?
So does that mean that the energy of a particle is also relative to the observer?
Absolutely. You didn't think you were going to get off that easy, did you? That the energy and momentum wouldn't depend on the observer? Listen, if the distance between two events and the time between two events depend on the observer, then that implies, among other things, that the velocity of a particle depends on who's observing it. We already saw that with the velocity addition formula. So then, it's not a large leap from there to say that the momentum, which, as you know, is usually just mass times velocity, should depend on the observer. The thing that's interesting is that the form of the momentum is not exactly the form that you would have expected. It's not just mass times velocity. Instead, it takes this form. And so what I'd like to do now is explain to you why it takes this form. So, in order to explain to you why the relativistic energy and momenta take this form, let me just remind for you the argument for conservation of energy, or momentum, in Newtonian physics. So let's consider an object which is not affected or not subject to external forces. Then in Newtonian physics, that means that the force on the object is equal to 0, so that the mass times the acceleration of the object is equal to 0, which of course is just the time derivative of the mass times the velocity of the object, or the time derivative of the momentum of the object. So that if an object is not acted on by any external forces, its momentum vector is constant in time. That's the statement that momentum is conserved for a system which is not acted on by any external forces. In special relativity, if you think about this formula for a second, you'll see that it must be the case that the form for the momentum has to be changed. Why is that? Well, the form of the velocity vector, and hence of the acceleration vector, is going to be frame dependent in special relativity. So, in order to understand this in a little bit more detail, consider just motion in one dimension, so I don't have to keep writing this vector symbol all over the place. so that we have some object whose position as a function of time is given by x of t, as measured in some frame S, where x and t are the usual position and time coordinates in that frame. And we also wish to describe the motion in another frame, S prime, where we would parameterize the position of the particle by writing down the function x prime as it depends on t prime. And then you could talk about the velocity, v, as measured in the S frame, which of course is just dx by dt, as compared to v prime, the velocity measured in S prime, which is vx prime by dt prime. And I'll consider the case, as is typical in special relativity, where the frames S and S prime are not the same, but are moving at some relative velocity to one another, which I will call u. So u is the velocity of the frame S prime with respect to S. And then, as we know, the coordinates of the x frame will be related to the coordinates of the S prime frame by the usual Lorentz transformation rule, which at this point should be second nature. And among other things, this allows us to derive the formula for velocity addition, namely the formula for the velocity v in the S frame, as it depends on the velocity v prime, the velocity in the prime frame, and u, the relative velocity of the two frames. So this is v prime plus u over 1 plus u v prime over c squared. And one can see that just by taking the derivative of this equation, or comparing those two equations as equations for dx and dt in terms of dx prime and dt prime. Okay. We saw that in order to think about forces, we need to understand not just how velocity changes between frames, but also how acceleration changes between frames. So let's define A to be the acceleration of this object as measured in the S frame. So that's dv by dt. And A prime to be the acceleration as measured in the S prime frame, which is dv prime by dt prime. And just as v can be determined by v prime and u, A can be determined by A prime and u. And all one needs to do then is just work out the relatively straightforward, but as we'll see, a bit lengthy computation involving this change of variables between S and S prime. So that's what I want to do right now. And essentially all I will need to do is use this formula for velocity addition, use the Lorentz transformation rule, and carefully use the chain rule several times. So A is dv by dt, which by the chain rule is dv by dt prime times dt prime by dt. All I'm doing here is changing my dependent variable from t to t prime. So how do we compute that? Well, that's the product of two terms. The first of which, so dv by dt prime is found by taking the t prime derivative of that equation there. So what is that? Well, v prime is a function of t prime, and in particular, dv prime by dt prime is what we call A prime. So this will be A prime times the derivative of this expression here on the right-hand side with respect to v prime. So what is that? Well, there's a term that comes from taking the derivative of the numerator v prime plus u. So that's 1 over 1 plus u v prime over c squared. And then a term that comes from taking the derivative of the denominator. So we get the square of the denominator. And then in the numerator, we have the derivative, we have the derivative of the denominator with respect to v prime times v prime plus u. We can collect those terms. We get a prime divided by 1 plus u v prime over c squared quantity squared times 1 plus u v prime over c squared coming from this first term minus v prime plus u times u over c squared. And you can see here that the v prime times u terms will cancel, and we get a prime times 1 minus u squared over c squared divided by 1 plus u v prime divided by c squared quantity squared. I try to be careful here to make sure my u's are very curvy so that they look different from my v's. If there's a formula that's not entirely clear here, please let me know. Okay, so that was one of the terms in the acceleration. In order to determine the other term, which is this term here, dt prime by dt, we just have to remember that this is the inverse of dt by dt prime. And dt by dt prime, here, let me give myself a little more room down here. dt by dt prime is using the Lorentz transformation rule. So t is gamma t prime plus u over c squared x prime. So if you take the derivative of that with respect to t prime, you get a gamma out front. The derivative of t prime with respect to t prime is 1. And we have u over c squared times x prime. And the derivative of x prime with respect to t prime is v prime. So, putting it all together, the acceleration is dv by dt prime, which is a prime, times 1 minus u squared over c squared divided by 1 plus u v prime divided by c squared squared. And then when we multiply by dt prime by dt, we just get another factor of 1 minus u squared over c squared on the top, so that becomes a 3/2, and another factor of 1 plus u prime v prime in the denominator, so we get a factor of 3 in the denominator. And so what we have derived here is the formula for how accelerations change as you go from one frame to another. Any questions so far? So if all of my derivatives and uses of the chain rule have been a little fast, I encourage you to go through and work through this derivation again in the privacy of your own home. Questions? Yes.
I'm sorry about that. I'm not sure where you said it can be.
Sorry. Good. Okay. So what was the acceleration? The acceleration is dv by dt. So I'm looking at this formula here. dv by dt prime times dt prime over dt. And dt prime over dt is the inverse of this guy here. Okay. Which means you get another factor of 1 plus u v prime over c squared in the denominator. So we had 2 factors from this equation and 1 factor from this equation. Total of 3 factors of 1 plus uv prime over c squared in the denominator. Another question. I'm now going to use this in a very clever way. So, the object that I'm considering obeys some trajectory that depends on time. So that means that the frame where this object is at rest will, in general, not be moving at constant relative velocity with respect to another frame, if the object is subject to some accelerations or something like that. But what we could do is we could take S to be the instantaneous rest frame at some time t. So let's fix some time t, and then choose the frame where the object has velocity 0 in frame S at that time t. What does that mean? That means that at that point v is equal to 0, or in other words, v prime is equal to minus u. Remember, because v was v prime plus u over some denominator. So at that point, the relationship between those 2 accelerations, just plugging in u is equal to minus v prime in the above expression, we get a is a prime times 1 minus v prime squared over c squared to the 3/2 power. Using the fact that v prime squared is the same as u squared, because the minus 1 will then square to 1. Okay. So let's think about this expression for a second. Okay, otherwise known as dv prime by dt prime times 1 over the 3/2 power of 1 minus v prime squared over c squared. So let's consider a particular example. Let's consider the case where a is equal to 0 at some moment in time. A being the expression for the acceleration as measured in the S frame. Then in that case, momentum should be conserved. Indeed, in the S frame, we have an object that is not moving, its velocity is equal to 0, and it is not accelerating. So I should be able to use the standard Newtonian form for the force law. And indeed, A being dv over dt is equal to 0 will imply that v is a constant. And in particular, m times v is a constant. But what does this look like in the S prime frame? Well, if there's something conserved in the S frame, there should be something conserved in the S prime frame. And in order to determine what it is, we can stare at the right-hand side of that formula. The statement that something is conserved is the statement that the time derivative of something should be equal to 0. And in the S prime frame, the time derivative that we're interested in is d by dt prime. So the question is, if a is equal to 0, does the right-hand side there look like d by dt prime of something? And if you stared at it long enough, you could figure out the answer. But this class is only 50 minutes long, so let me give you a little hint. Let's consider d by dt prime of v prime divided by the square root of 1 minus v prime squared over c squared. What is that? Well, v prime depends on t, so this is dv prime by dt prime, times, well, from the numerator, so the whole thing will have a power of 1 minus v prime squared over c squared to the 3/2 power in the denominator. And the numerator is going to be, well, just a thing first that you get by taking the derivative of the v prime. So that's 1 minus v prime squared over c squared minus the thing that you get from taking the derivative of the denominator. So you get a factor of minus 1/2 because you're taking the derivative of something to the minus 1/2 power. That cancels a factor of minus 2 because you're taking the derivative of minus v prime squared in the denominator there. And so we get plus a v prime squared, taking into account this factor of v here, over c squared. And we see that the second and the third terms in the numerator there cancel. And so this is nothing more or nothing less than what we called then the right-hand side of this equation. So dv prime by dt prime times 1 over the 3/2 power of 1 minus v prime squared over c squared. So, the statement that the velocity v is conserved in the frame S is the same as the statement that the quantity v prime over the square root of 1 minus v prime squared over c squared is conserved in the S prime frame. Now, in the S frame, the object wasn't moving at that moment t in time. But in the S prime frame, it was moving. And it was moving at some potentially relativistic velocity. So that means that we can identify this quantity as the quantity which is going to be conserved in under the laws of dynamics. And it's typical to multiply this by the mass of the system and identify the conserved momentum as the mass times this combination of velocities, or just gamma mv, otherwise known as mv over the square root of 1 minus v squared over c squared, as the conserved momentum in special relativity. And I've restored here the vector symbol, so I considered in the example above only one-dimensional motion, but of course one could generalize this to three-dimensional motion if you liked, and that vector symbol would just sort of go along for the ride. I should make a note here. Actually, if you look in Morin's book, he gives a completely different derivation of relativistic momentum and why it has to take this form. I like this derivation better. If you aren't happy with it, I recommend that you look at the derivation in the beginning of chapter 12 of Morin's book. It's slightly different in flavor. Frankly, I found this one simpler. Questions? Yes? Yes. So, sorry. Maybe I don't quite understand your question.
If you go back to the acceleration and you put a prime on
Yes.
the
Oh, you're asking about the case where a is non-zero?
where a is
Where a is 0. Yes, that's the case we're considering here. So a is 0, so dv by dt is equal to 0. We're asking what that would look like in the frame S prime. Is there a quantity whose derivative is 0 with respect to t prime, the time in the S prime, right? So the question is what? Yes. So, for example, dv prime by dt is also equal. Sorry, dv by dt prime is also equal to 0. But that's not a quantity that you would measure as an S prime observer. You would measure dv prime by dt prime. And the difference between those two terms, that's actually a good question, is precisely what leads us to identify this slightly different version of the conserved momentum. That's a good question. Yeah. Question?
Maybe it's just a error from U to V, but I see a jump from like U squared to V squared. I don't know where.
Remember that V prime is minus U. So V prime squared is U squared. Yeah, no, I'm using that fact. Good question. Good. Okay. And just as we, in Newtonian mechanics, have the law F equals ma, in relativity, the law F equals ma is replaced by the law F is d by dt of P, which is gamma mv. Okay. That's, I suppose, implicit in what I was saying above. But when we consider forces in special relativity, we expect them to obey an analogous version of Newton's third law. I guess that Newton's third law? I never remember which one's which. It's one of Newton's laws, between 1 and 3, 2 plus or minus 1. So F would be the time derivative of the relativistic momentum. And then, given this really definition of what we mean by force, there are a couple different ways that we can understand why the appropriate relativistic notion of energy is gamma mc squared. So I'll present two different derivations of this because it's a very important formula. So to see the conservation of E equals mc squared divided by the square root of 1 minus v squared over c squared, or just more simply, the conservation of gamma mc squared, where gamma is our old friend, the relativistic factor, then we need to use the conservation of momentum. So, one way of seeing this is to write down this expression for the force in a little bit more detail. So this is d by dt of gamma mv. And as we just saw above, so this is the exact calculation that we did above. This is dv by dt times gamma cubed. So all I'm doing here is repeating the statement that I derived above. I'm just repeating this statement here with this factor of 1 over minus v squared over c squared to the 3/2 power, otherwise known as gamma cubed. So that means that the work that is done during some process where a force is applied to a particle, well, I remind you that the work is the integral of f dx. If you move a particle from one point to another using some force, then that does some work, which is the integral of the force between the 2 points. So, in principle, I should really put vector symbols on this and be taking a dot product here, but I'll just consider again motion in one dimension to make life simple. Then using the above formula, this is the integral dx of gamma cubed times dv by dt times dx. And I could then make the following very clever change of variables. So here I'm regarding the different points on the trajectory of the particle as labeled by the position of the particle x. But I could also label them by the velocity of the particle, v, and I could use the fact that v is equal to dx over dt to rewrite this formula as the mass times the integral of gamma cubed times dv times dx over dt. What have I done there? I've just moved the dt from here over to here. Okay. If you don't remember, if you want to say it formally, what I've done is I've done a change of variables from x to v and introduced the Jacobian in that change of variables. But if you want to just remember the rule for how it works, you just move these dt's around just like they're normal numbers. Those are the rules. There's a reason why we call derivatives d something by d something, and we call the integration measure d something. It's precisely because you can manipulate them according to the standard rules for fractions. So this is otherwise known as the mass times the integral of v over the 3/2 power. So v being dx by dt. This is the 3/2 power, 1 minus v squared, c squared to the 3/2 coming from the gamma cubed dv. And that's an easy integral to do. It's just mc squared divided by the square root of 1 minus v squared over c squared plus a constant. How do I know how to do that integral? Well, you can just check that the v derivative of this quantity that I wrote down here is precisely what's appearing here. In fact, that's exactly the same computation I did above. And remember that the work that is done during some process is otherwise known as the change in energy. Delta E during that process. So that is at least a bit of a justification for defining the energy of an object to be mc squared divided by the square root of 1 minus v squared over c squared. And this constant term that appears here on the right-hand side of this equation, I remind you that whenever you define the energy of a system in Newtonian mechanics, we never actually care about the absolute value of the energy. We only care about relative values of the energy for two different configurations of the system. So, for example, I could talk about the dynamics of all of the energy of the particles in this room, okay? And so each particle in this room would have some energy. I could add 1,000,000 to that value of the energy, and that would not change my description one bit. Another way of saying that is that if I want to talk about the gravitational potential energy of some box of chalk here, I could either say that the gravitational potential energy is 0 when I'm holding it up here, and then it's negative when it's down here, or I could say that it's 0 here, and it's some positive value here. And as long as all I'm doing is adding an overall constant to the energy, then it doesn't matter. And so I'll just choose my constant so that the energy is gamma mc squared. And with this definition, the force will obey the usual law that the force is the minus the derivative of the potential energy of some system. That's just the usual statement that the work done, i.e. the change in the energy of the system, is the integral of the force. Actually, is the work minus the integral of the force? I never quite remember. Okay, I can't remember those signs there. Work, who remembers the definition of work? There's a reason why I don't teach freshman physics. Okay. This derivation is a little formal for my tastes. So it's possible to give a slightly different, somewhat more sophisticated derivation, which is something maybe that I'll do at the beginning of class next time. But I would just like to make one more point, which is that we can compare this to our Newtonian physics. By considering objects or cases where the velocity is much less than the speed of light. So then the energy, which is mc squared over 1 minus v squared over c squared, can be Taylor expanded. So we just Taylor expand the denominator in powers of v over c. So we get 1, so there's a 1/2, plus 1/2 coming from the Taylor expansion of 1 over the square root. V squared over c squared plus higher order terms. So that the energy is mc squared plus 1/2 mv squared plus terms that are of order v to the 4th over c squared times the mass. Or I'll just say plus higher order terms. So what do we see here? What we see here is in this formula, we indeed have the usual kinetic energy in Newtonian physics, and we have shifted it by a constant which we refer to as the rest energy of the object. And indeed, you see that with this identification, when v is equal to 0, we have the famous identity E is equal to mc squared. So in this formulation, we attribute an energy to an object at rest, which is non-zero, and in fact, which is fantastically large. It's the mass of the object in units of c squared. Just one more definition before I end. So we sometimes define the rest energy of an object just to be mc squared, and the kinetic energy of an object to be the relativistic energy gamma mc squared minus the rest energy. So that would be gamma minus 1 times mc squared. So that's just the usual 1/2 mv squared in the limit where the velocity is very small compared to the speed of light, but it will have some corrections in powers of v squared over c squared for relativistic objects. And sometimes people even define a relativistic mass, which is gamma times the rest mass. I would prefer just to talk about the relativistic energy, which is just gamma mc squared, instead of using the terminology relativistic mass, because I'd like to reserve the word mass for the rest mass of an object. But in some treatments, you will see people talking about things like the relativistic mass. Okay, I'll see you guys on Wednesday. Go ahead and pick up the first problem set, which has been graded. I have solutions here of the first problem set for you to pick up. And problem set 3 due Wednesday if you haven't picked it up yet.